The Sieve of Eratosthenes, a new section. Eratosthenes was a Greek philosopher, mathematician, physicist. He was the director of the famous Library of Alexandria, which got destroyed in a fire. Okay, at one point, some people attacked. Not going to discuss about that. See, people who kill others are bad enough already, but people who destroy knowledge are the enemies of the whole of humanity. But anyway, among the many remarkable things that this man did, he calculated the circumference of the earth using only simple Euclidean geometry, and the figure that he got is very close to what we now have. And this is another of his inventions. So we will see what it is. So let us start the section. The section starts with a property of composite integers. Say A is a composite integer. A is greater than 1, of course. We are not considering negative integers. Then A can be factorized non-trivially as B times C, where B and C satisfy these inequalities. That means these are both non-trivial factors of A. Now, of course, B is either less than or equal to C, or B is greater than C. Without loss of generality, we can assume that B is less than or equal to C. Now we can multiply on both sides of this inequality by B, and we can do so because B is positive. Okay, had B been negative, then also you can multiply on both sides, but the inequality will get reversed. In this case, the inequality will not get reversed, and you will have this, and BC is A. Now again, because both B and A are positive, so we can take square roots on both sides, obtaining this inequality. So you see that at least one of these two factors of A has to be less than or equal to the square root of A. Now you look at this inequality. B is greater than 1. So B is a positive integer greater than 1. So by the fundamental theorem of arithmetic, B itself has a prime divisor. So there exists a prime which divides B. Now because P divides B, in particular P has to be less than or equal to B, which means that P also has to be less than or equal to the square root of A. Now P divides B and B divides A, so at the same time P also has to divide A. So what is the conclusion of all these things? From these calculations we conclude that if A is composite, then A has a prime divisor P which is less than or equal to the square root of A. But what is the big deal about this? This property can be used for this purpose. Say you are given some concrete number A here, and you want to know whether it is prime or composite. Now because of this property, you know that if A is composite, if A has to be composite, then there must be a prime divisor of A that does not exceed the square root of A. Without this property, how would you proceed to show that, for example, A is composite or prime? Naturally, you would look at these integers and see if any one of them divides A. If any one of them divides A, then A is composite. Otherwise, A is prime. But you can see that as A increases, A becomes larger and larger. The number of integers here to be checked also increases. So the task eventually becomes prohibitively long. Okay, computationally daunting. Now this property reduces that task to some extent. You need not look for factors of A all the way up to A minus 1, but you can stop at square root of A or before that. But even then, as A increases, so does the square root of A. So ultimately the task remains computationally challenging, but nevertheless there is some amount of reduction in the work. But that is not the main point why we are looking at this. For some fairly small A, this will allow us to see whether A has a factor or if A is a prime. So let us look at an example. Okay, but then we will see how this property can further be used to obtain this thing, the sieve of Eratosthenes. That's why we have those numbers here. Okay, I cannot clean that part right now. So now let's look at a concrete A and see how things work in that case. So the A that the author has taken is 509. It turns out that the square root of 509 lies between 22 and 23. So by the property we have seen now, if no positive integer, in fact if no prime that lies between 2 and 22 divides 509, then it has to be prime. You follow the logic. You recall what we did just now. If A is composite, then there exists a prime less than or equal to square root of A that divides A. This implication is equivalent to its own contrapositive, which is what the negation of this implies the negation of this. Negation of this means what? That for all prime satisfying this inequality, none of them divides A. Implies, what is the negation of this? A is not composite, that means A is prime. So if we now look at the primes that do not exceed this and none of them turns out to divide 509, then we would conclude from this contrapositive that 509 is then a prime. So what are the primes that lie in this part? 2, 3, 5, 7. The first few we of course can remember: 11, 13, 17 and 19, and that's just it. Okay, and it turns out that actually none of them divides 509, which can be verified of course, and that is why 509 is a prime. So you can see that in this particular case the task has actually been significantly reduced. Imagine instead of this looking at all the primes lying between 1 and 509, that itself is a challenging task because you don't know. I mean, I'm not saying you don't know all the primes. You may know, there may be a list available to you, but if you don't know, normally we know the first few primes, right? But after some stage we really don't know. The number theorists know them by heart, I don't know, but we do not know that many. So then what you do? If you do not know the primes, then you have to look for divisors starting from 2 and ending at 508. You can see how many numbers that is. Okay, so that's why this is a significant reduction of labor. But unfortunately, as I said just now, as this number increases, so does the square root. So these available primes that you have, which are less than or equal to that square root, that itself will increase in number, and soon you will face that same problem. But anyway, for fairly small values, it works pretty well. Now this fact can also be used. You see, this is in one direction. 509 is a prime, and we have just now verified that it is a prime using this property. But if we have a composite integer, then we can also use this property to find its canonical factorization. So this next example is about that. It works both ways, with primes as well as composites. So this is example 3.1, and the number that we now have is 2093. And first of all, we look at its square root, and it turns out that the square root lies between 45 and 46, and the primes that you have before 45 are these: 11, 13, 17, 19, 23. Then see, already I am struggling. 23, yeah, then the next one is 29, then 31, 37, 41, 43. 39 is not a prime because it's 3 times 30. 43, and that's it. So these are all the primes that are less than or equal to square root of this number a. Now if one looks looks at all these integers and checks everyone for a factor of the given number, then one quickly finds out pretty quickly that 7 is actually a factor. And the factorization is this: 7 times 299. We know that 7 is a prime, but what about 299? You can then repeat this process with 299. And if one proceeds accordingly, first of all, you have this. So now you have to, in order to search for a prime factor of 299, if there is any other than 299, because it may also be a prime itself. Right now we don't know, but in search for that, if it is composite, it must have a prime factor less than or equal to 17. So those primes already are there, many more are there, but these are already available here. And in search for a factor of 299 in this region, one finds that 13 is a factor, and one finds this 13 times 20, is it 23 or 29? 23. So that's how we see that 299 is not a prime actually, but it's a product of 13 and 23. 13 we already know it's a prime, but 23 also turns out to be a prime. So the canonical factorization of our given integer is 7 times 13 times 23. What is the advantage of our method? The advantage is that we did not have to look at all the primes reaching 2093. We only needed this many primes. Okay, so this is another application of that property of composite integers in finding out the canonical factorization of a composite integer. Just like there we used it to prove that the previous number is a prime. Now, using this property of composite integers, Eratosthenes devised a scheme which allows one to effectively calculate all the prime numbers less than a given number. That's what the sieve is. To describe what the sieving process involves, let us consider this. Say your number is n. Say you have the integer n, and you want to know all the prime numbers lying between 1 and n. That's because in order to apply this property of composite integers, you actually need more primes, right? Now, how will they themselves be generated? So that question can be answered by the sieving process. So it goes like this. So what will you do? You look at only the primes that do not exceed the square root of n. Okay, but you may ask that I may not know these also. I mean, I may not know all of these primes fully. What do I do? See, the thing here is this. What we are going to do is this. Suppose you identify one such prime. Forget about finding all such primes p which satisfy this inequality. Forget about all right now, okay. Say you have a prime p that satisfies this inequality. What you are going to do, among all the integers starting from 1 and well, you can discard 1 of course, because 1 does not contribute to anything. Starting from 2 and all the way up to n, among all those integers, you strike out all these multiples of p. P itself, of course, you keep p in your list, but you strike out the higher multiples of p. Why? Because they are already clearly composite. As many as you have which are all less than or equal to n. Okay. Then you find another such prime, you strike out its multiples. But then what is the guarantee that all the composite integers will be discarded in this way? Let us see what the reason is behind that. Suppose in this process, it's a sieving process, right? You are trying to keep some things, but you are trying to discard some other things. The things you want to discard are the composite integers, and you want only the primes to remain. You want all the composite integers to fall through the sieve, and you want the primes to be like large particles which remain on the sieve. So suppose there is a composite integer a that satisfies these inequalities. So what is the guarantee that a will be striked out in this process? You see, because a is less than or equal to n, the square root of a is less than or equal to the square root of n. So what are we doing in this process? We are weeding out, we are removing all these multiples of p, where p is what? P is any prime less than or equal to n, right? And in that process, all the you see, if your a itself is composite, then it also, by our property, has some prime q less than or equal to the square root of a, right? Because that's what that property says. If a is composite, then it has a prime factor which does not exceed its square root. But then that q is also a prime of this type. So in our process of removing multiples, higher multiples of the primes that do not exceed square root of n, except the primes themselves, at some point the multiples of q will also appear. So you will see, we will see the process actually working here, that a will also be striked out. Why? Because when you remove the higher multiples of q, one of them is a itself. So a will also be striked out. So that's how in that process, no composite integer satisfying these inequalities will survive. Okay, they will fall through the sieve, and whatever remain, they are the prime numbers not exceeding n. So let us now see the process and try to find out all the prime numbers between 1 and 100. 1 of course need not be written. So the first prime that we actually know of in this process is 2. So we are now going to weed out, we are now going to strike out these multiples of 2, keeping 2 itself of course, and we strike out, that means all the even numbers greater than 2 that we are going to strike out. And the author is actually using different ways of striking out things, multiples, in order to show which primes are being used. So all the even numbers greater than 2 are striked out like this: 12, 14, 16, 18, 24, 26, 28, 30. There is no room for error. I should do it carefully. 52, 54, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 82, 84, 8, 90, 92, 94, 96, 98 and 100. Okay, so that means they are already gone. But anyway, let's just keep them. Let's not wrap them up or anything like that. But I will now need some space to calculate the multiples of the other primes. Other primes means how do I know what the other primes are? In your process, you just go like this. You have started at 2 and you did whatever you did with 2. But then you come back and see what survives. What survives that process? The first number that has survived this first attack is 3, which turns out to be a prime. Okay, we already know that 3 is a prime. So next we are going to beat out the multiples of 3 other than 3 itself, and they will be striked out like this. So 6, 9, you see a new number is being striked out now. "21, 24, 45, 57, then 60, 63, then 22, that means 66, 23, 69, okay, 24, 72, 25, 75, 26, 78, 27, it will be 81, 81, then 28, 84. I hope I am doing it correctly. Okay, we will see ultimately. 87, 30 is 90, of course, then 31, 93, 32, 96, 33, 99. So all the multiples of 3 other than 3 itself have also been striked out, and among them some were striked out before when we striked out the higher multiples of 2. Then in this process next comes 5. Okay, and you know that 5 is a prime. And in fact what we said before the beginning of the process is this, no? You beat out all the multiples of those primes that satisfy this inequality, and our n now is 100. So we are looking at these primes. So actually we are looking at the multiples of these only. So you see that actually we have to work with only 4 primes. So yes, we do need to know all these primes beforehand. But do you see the advantage of this process? Although right now we are in the middle of the process, but at least we can see that once we do this for 1 to 100, then we already have many primes. Okay, so that list is there, but then if you go from 100 to 1000, okay, say you next want to find all the primes between 100 and 1000, then you would have to weed out multiples of p that are less than 100, but this process itself will tell you the primes that are less than 100. Okay, so you can use them, and like that, step by step you can create more and more primes. Now this itself will become computationally heavy, but a computer can do it, right? Anyway, so let's carry on the process. So we have strike out the multiples of 2 and 3 in this way. So next comes 5. 5 is very easy. Multiples of 5 are very easy. To strike out the multiples of 5, the author has used horizontal bars. $15, $25, $30, $40, $45, $55, $60, $65, $70. Easy I say because the numbers which are multiples of 5 have their last digits either 0 or 5. That's it. $85, $90, $95, $100. And finally, it's 7's turn. And for 7, we are going to use a wavy symbol like this, a tilt. So 7, 14, 20, 28, 35, 49, 56, 63, 70, 77, 84. Then what? Wait, what? I think I lost count. Or maybe I made a mistake. Oh, okay. Yeah, I calculated the product wrongly. Yeah, I think that's just it, no? So what are the numbers that are left behind? Let's circle them. 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, next 53, 59, 61, 67, 71, 73, 79, 83, 89, 97. Okay, let me now see whether I am correct. 2, 3, 5, 7, 11, 13, 17, 19, 29, 31, 37, 29, 31, 37, okay, then 41, 43, next 47, 53, 47, 53, okay, then 59, 61, 59, 61, next 67, 71, 73, 67, 71, 73, 79, 83, 89. 79, 83, 89, and finally 97. So these circle numbers are the primes lying between 1 and 100. Okay, so I got it a little wrong in the beginning. We do really need to know all the primes less than the square root of n. But as I have just now said, now you have these primes, okay, which lie between 1 and 100, and you can now use them to run the process again to find all the primes less than 1000, and then you can continue this, okay, quite a few times. If you want, you will then get many more primes. So you see that the task of finding all the primes up to some number, if you think about it, in general it seems like a daunting task, but using the sieve of Eratosthenes, it can be done. We have done it right now here, right? It did not take extremely long, we just have to be careful. So that's how we have found all the primes. Now after this there are other things, of course, and after this, in fact, that famous proof of Euclid comes, which shows that actually there are infinitely many primes. But we will continue with that in the next number theory update. So that's just it for tonight. Tomorrow, of course, we have our usual community post, and we are going to solve some algebra problems from Lee's algebra. So see you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.